Dear students, welcome to the second lecture on countability. So here I start with one simple lemma. It says, so let X be a non-empty countable set and let f x to y be a surjective function. Then we prove that y is also countable. The proof is actually simple. Now since X is a non-empty countable set, so there exists a surjective function G from the set of natural number to X, right? That's mean we have n to x a surjective function G and x to y we have a surjective function f, and then we know that the composition of two surjective function is also surjective. Then f composition G, this is a surjective function from n to y. We can write this is a surjective function. Therefore, y is countable. Right? Now by using this we shall prove that the set of integers and the set of rational numbers are countable. We can write it is as a theorem. So first of all, the set of integers Z is countable. So there are several ways to prove this one. So here I shall prove this one by union of three countable sets. So first of all, define Z minus as a the set -1, -2, -3 in this way, right? Then if we define a map f from n to z, z minus by x going to, or you can say n going to minus n is a bijection, right? Therefore the set that z minus is countable, right? Now we can write z as union of the set of natural number union 0 union z minus. Now since z is union of three countable sets, therefore Z is countable. Fine. Now there is another result. We prove that the set of rational numbers is countable. Again, there are several ways to prove this one. So here I shall prove with a simplest way. So first of all, we define say q plus equal to, so let this equal to m by n, where m and n are relatively prime natural numbers. Okay, and we also define say q minus is minus m by n, where m and n are again relatively prime natural numbers. Okay, then q is written as q plus union 0 union q minus. Now if we can show that q plus and q minus both are countable, then q being an union of three countable sets is also countable, right? Now we prove that q plus is countable. So first of all, we know that n cross n is countable, right? Why it is countable? It is a product of two countable sets. We can write here being a product, or you can specify being a Cartesian product of two countable sets, right? Now if we define a function f from n cross n to q plus defined by m comma n, this ordered pair going to m by n, or you can say f of this is equal to m by n, then this function is a surjective function, right? Now since n cross n is countable, that imply q plus is countable, right? Again, if we define n cross n to q minus defined by f of m comma n equal to minus m by n, then this function is a surjective function, right? Now that imply q minus is also countable, right? Therefore q is a union of three countable sets, hence q is also countable, is also countable. We can write here being an union of three countable sets. Fine. Now in the last lecture I asked if you have a product of countable number of finite sets, then what will be the resulting set? Is it countable? And I told that it is no. So it is uncountable. Now I shall prove that. So my next theorem is the set, if you take only two element set, product with again two element set, this one. Now we prove that this set is uncountable. So this can be denoted as this set. So 0, 1 power n. Fine. Now we prove this result. So here is the proof. First we assume that if possible, let the set X be countable. Okay. Now since X is countable, so there exists a surjective function say f from the set of natural number to X, right? Therefore the set X can be written as an infinite sequence, say x1, x2, x3 in this way, where the xn is actually f of n for all n belongs to natural number, right? We have already seen that. So if we have a countable set, then that countable set can be written as an infinite sequence, right? Now we prove that there is no such surjective function. That means we shall find one element from X which does not have any preimage. That means this map is not surjective. Okay. So first of all, what is my x1, x2, x3, all of these elements? So each xn is also a sequence with the entries 0 and 1, right? So now let x1 equal to that infinite pair, say x11, x12, x13 in this way. Say x2 equal to x21, x22, x23. Say x3 equal to x31, x32, x33 in this way, and it is going on. So I can write xn as well. It is xn1, xn2, xn3 in this way, right? Where you can say each of xij belongs to the set 0 and 1. That means each of xij either 0 or 1 for all ij belongs to natural numbers. Fine. Now we shall construct one point in X which does not have any preimage. So we consider, so let y it is a sequence with the entries of 0 1, say right, it is y1, y2, y3 in this way, okay, where yn equal to 0 if xnn equal to 1, and this is 1 if xnn equal to 0. Okay, in this way we construct one element, that is one sequence with the entry 0 and 1. Obviously y is an infinite sequence with the entry 0 and 1, right? Now you can see that since y is a infinite sequence with the entries of 0 1, that imply y belongs to x, right? Now you can check that y not equal to x1. Why y not equal to x1? Because what is the first term of y? It is y1, and first term of x1 is x11. But see, x1 and x11 and y1 is not same, right? Therefore x1 and y is different. Similarly, you can check that for each n, right, yn is not equal to xnn, right? Thus we can say nth entries of xn is different from the nth entries of y, right? Therefore y not equal to xn for all n belongs to natural number. That's mean we have constructed one infinite sequence with the entry 0 and 1. That's mean we have found one element y in the set x, but x, the point y, is not in this list. That's mean the point y does not have any preimage. So therefore we can write here f of n not equal to y, since xn equal to f of n, right, for all n belongs to natural number. Thus y belongs to x, but the point y does not have any premise under the function f. Thus f is not surjective. So this is a contradiction. Right? So we assume that x is countable and we get a contradiction. Therefore x is not countable. So x is uncountable. Fine. Now similarly we can prove that the set of all real numbers R is also uncountable. The proof is almost similar to that. So first we prove the set closed interval 0 1 is uncountable. Okay, so here is the proof. First we look at the decimal representation of each element of the closed interval 0 1. Decimal representation of each elements of 0 1. Now look at most of the elements from closed interval 0 1 has an unique representation, that is unique decimal representation, but some of the element, in fact countable number of elements, does not have unique representation. It has two representations. For an example, so some of the elements of 0 1 has exactly two representations. For an example, we can see, say 0.2, we can write it is as 0.19999, it is going. Even if we have 1, we can have 0.9999. This one, it is same as 1, right? So if we have 1 to say 7, it will have 0.1269999 in this way. Now let X be the collection of the set 0 and all possible non-terminating decimal representation of, or we can say of, the elements of open 0 closed 1. Okay, that's mean in this collection X we consider 0 and we will not consider 0.2, we will take this representation. We will not take 1, we will take this representation, and we will not take this, and we will take this representation, right? So in this way we will take my set X. That's mean X actually closed interval 0 1 and each element of X has a unique decimal representation. Decimal representation. Okay. Now we assume that if possible X is countable. So if possible, let X be countable. Then there exists a surjective function f from the set of natural number to x, right? That is, x can be written as an infinite sequence. Say x1, x2, x3 in this way, right? Where xn is actually f of n for all n belongs to natural number. Okay. Now we prove that this listing is not complete. That's mean we shall prove that the function f is not surjective function. So we shall find one element, say y, from the set X such that y does not have any preimage under the map F. So first of all, what is my x1? So x1 has an unique decimal representation. So x1 is equal to 0. Say x11, x12, x13, x14 in this way, and x2 can be written as x21, x22, x23, x24. Similarly, x3 can be written as 0. x31, x32, x33, x34 in this way, and so on. Right? Okay. Now here the xij belongs to the set 0, 1, 2 up to 9. Right? Now we find one element. Say let y equal to 0. y1, y2, y3. This is an element defined by such that we say yn equal to 0 if xnn is not equal to 0, and say it is equal to 1 if xnn equal to 0. Right? That's mean we construct one element y which is 0. y1, y2, y3, y4 in this way, and yn is not equal to xnn. Right? Now since y is a decimal representation of a 0, 1 sequence, therefore the element y belongs to closed interval 0, 1, and yn not equal to xnn for all n belongs to natural number. But we have assumed that x is the collection of the unique representations of the elements of 0 and 1, right? Therefore, if y is equal to some xn, then all the term should be same. But here nth term of y is say different from the nth term of xn, and this is true for all n. Now since each element of x has unique decimal representation, so we can say that y is not equal to xn for all n. In other words, f of n is not equal to y for all n. That implies y belongs to the closed interval 0 1, but y does not have any pre-image under the function f. Therefore, f is not surjective. But we assume that x is surjective, right? So this is a contradiction. So we assume that the set x is countable and we get a contradiction. Therefore, x is uncountable. Now what is the set x? Since x equal to 0 1, that means x is the collection of all the unique representation of the element 0 1, right? Therefore, we can say closed interval 0 1 is uncountable. Okay? Fine. Now from this we have a trivial corollary that R is uncountable. Why R is uncountable? Because if R is countable, then the closed interval 0 1 is a subset of R, so it should be countable, right? But this is a contradiction. Therefore, R must be countable, because if R is countable, then being a subset of a countable set closed interval 0 1 will also be countable, right? But this is a contradiction. But this is a contradiction. Therefore, the set of real number R is uncountable. Okay. Now I define one important concept called algebraic and transcendental numbers. So a real number is called algebraic number, and algebraic number if it is a root of a polynomial of the form, say a0 plus a1x plus a2x square plus dot 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 plus an x to the power n. Okay, where each of ai belongs to Z for 1, so 0 less than equal to I less than equal to n. Okay. Now what is a transcendental number? Now if a real number is not algebraic, then it is called a transcendental number. That's mean, so a real number is said to be transcendental if it is not algebraic. Right? Now we have one interesting result. It says the set of all algebraic numbers is countable. And it will follows that the set of all transcendental number is uncountable. Okay, so here is the proof. So first of all, we assume that my Pn is a collection of polynomials of degree at most n. Okay, now then or you can say there is a surjective functions f from z cross z cross z, this is n plus 1 times, okay, to the collection Pn is defined by a0, a1 up to an is going to a0 plus a1x plus a2x square plus up to an x to the power n. Okay. Now since we have a surjective function from z power n plus 1 to Pn and the left hand side set is countable, so Pn is countable, right? So we can write here, since say z cross z cross z, this is n plus 1 times, so we can write it is as a short form, say zn plus 1, okay, is countable. Why this is countable? Because it is a finite product of countable sets, right? So Pn is countable. right? That's mean the collection of polynomial with integer entries, right, up to the degree at most n is countable. Okay. Now note that if you take each polynomial, right, each polynomial has maximum finite number of real roots, right? So we consider Rn be the collection of real roots of the polynomials in Pn. Okay. So now we can write that one. So since for each polynomial we have only finite number of real roots, so Rn is also countable. So Rn is also countable. Why it is countable? We can write here, being a countable union of finite sets. Is it clear? Okay, I can explain a little bit. So for an example, suppose Pn equal to union over I equal to 1 to infinity Pn I x, right? We know that Pn is a collection of polynomial of degree at most n, right, and the entries from Z. So we know that this is a countable collection. So that's mean we have written here in this way, where each Pn ix is a polynomial, right? Now we know that each polynomial has a finite number of real roots, right? Now consider Pnix, this polynomial has this number of roots, say Rni, because it depends on n and I, right, from R1, then R2 with suffix ni, and suppose up to Rmi, it depends on I, right? That's mean each polynomial this has this number of roots. Therefore, we can write Rn as a union of these sets. Now you can see that Rn is a union of these finite sets, right? Therefore, Rn is countable. Now what is my all the algebraic numbers? Now the set of all algebraic numbers is same as union of n equal to 1 to infinity Rn. Now we know that each of Rn is countable, right? Therefore, and it is a countable union of the sets, countable sets, so it is also countable. Now since each Rn is countable, therefore the set of all algebraic numbers is also countable, being an union of countable number of countable sets, right? So the set of all algebraic numbers is countable. Now from this we can deduce that the set of all transcendental numbers is uncountable, because we know that R is the union of algebraic numbers and transcendental numbers, right? Now, if the set of all transcendental number is countable, then R is also countable. Right? Because we have already proved that the set of all algebraic numbers is countable. Right? Therefore, R being an union of two countable set is also countable, but this is a contradiction. Right? Therefore, we can say that the set of all transcendental number is uncountable. Is uncountable. Okay, fine. Now, by using this countability and uncountability argument, we can solve few problems from linear algebra as well. So, here I just want to prove two results from linear algebra. First of all, we know that Q, that is the set of rational number, is a field, right? Therefore, we can think R, that is the real number, the set of real number, as a vector space over the field Q. Right? Now, from this we have two questions. First of all, what is the dimension of this vector space? That's mean the vector space R over the field Q, what is the dimension of this vector space? And the second question is, what is the cardinality of the basis? Of the basis. First, we prove that this vector space has infinite dimension. So, claim this vector space is infinite dimensional. Why? Because if possible, suppose the vector space has finite dimension. Okay, so that's mean it has a finite basis. So let be equal to say E1, E2 up to En be a basis for the vector space, right? So we can write here for some n belongs to natural number. Obviously it has dimension at least some value, right? It should not be 0 dimensional. Okay, then each element of R, say V in R, can be expressed uniquely as V equal to, say, x1 e1 plus x2 e2 up to xn en, where this xn belongs to Q. Okay, and this expression is unique. Now since this expression is unique, therefore the map f from R to Qn, which is just q times q up to n times, where this x1 e1 xn en, it goes to x1 x2 xn. This map is a bijective function. This is a bijective function, right? You can check that it is a bijective. Since the expression is unique, therefore it is injective, and for each x1 x2 xn in Q we can always have an expression, therefore it is surjective. Now we know that Qn is a countable set, right? Because Qn is a product of finite number of countable sets, so it is countable. Now since there is a bijective function between Qn and R, so it gives R is countable. But we know that R is uncountable, right? So this is a contradiction. So we assume that this vector space, that is the vector space R with the field Q, that is over the field Q, is finite dimensional, and we got a contradiction. Therefore this vector space, so we can say the vector space R over the field Q is infinite dimensional. That's mean if you have a basis for this vector space, then that collection should be infinite. Now the next question is, what kind of infinite the set is? Is it countable or uncountable? Next, I prove that the basis set for this vector space is uncountable. Again, the proof is similar to this only. So first of all, we assume that, so if possible, let the basis B is countable. So let B equal to the set say E1, E2, E3, E4 in this way. Okay. Now we define the vector space say V0 is just spanned by 0 element, say V1 is spanned by E1, V2 is spanned by E1 and E2 and so on, right? Therefore, we can check that so V1 is properly contained in V2 and this is properly contained in V3 and so on, right? We can include V0 as well. And dimension of Vn equal to n for all n belongs to the set 0, 1, 2, right? Now you can check that since each Vn subset of R, so union of n equal to 0 to infinity Vn, this is also subset of R, right? Now what about the reverse? So let some x belongs to R, okay, then x can be written as a finite linear combination of this basis, right? Therefore x equal to some x1 e1 plus x2 e2 up to xn en for some n, right? So that implies x belongs to Vn. So therefore R subset of this union of 0 to infinity Vn, that is we can say R equal to union of n equal to 0 to infinity Vn. Fine. Now what about the vector space Vn? So we proved that each Vn is countable. We have actually proved that in the previous part, right? Anyway, I can prove it again. Now claim each Vn is countable. Why each Vn is countable? So what is my Vn? Vn is spanned by say E1, E2 up to En, right? That's mean each element x in Vn is uniquely expressed by x equal to x1 e1 plus x2 e2 plus xn en, where xi belongs to q for I equal to 1, 2 up to n, right? Therefore if we define the map f from Vn to q power n, that is it is product of n times of q defined by this x1 e1 plus up to xn en is going to the set e1 up to x1 up to xn. So this is a bijective function. Now since each Qn is countable, therefore Vn is countable. Right? So that imply R equal to, which is union of n equal to 0 to infinity, Vn is also countable. But we know that R is uncountable, right? So this is a contradiction. Right? So that imply, so we assume that it has countable basis and we get a contradiction. Therefore, the basis for this vector space is uncountable. Right? So what is the cardinality of this vector space? So we know that cardinality of natural number is strictly less than the cardinality of R, right? And here, since it is uncountable, so let first of all B be the basis, right? Now since B is uncountable, that's mean this, the cardinality of natural number is strictly less than the cardinality of B, right? And we know that the cardinality of the whole vector space is R, so it should be less than equal to R, right? Now we don't know about the relation between cardinality. In the next lecture we will know the relation between the cardinality, and then we, by the continuum hypothesis, we know that there is no other cardinality between the cardinality of natural number and real number. Therefore, by the continuum hypothesis, we know cardinality of B will be same as the cardinality of R. Okay, so in the next lecture we will know more on cardinality. So we stop here. See you in the next lecture.